Okay, so the last lesson for us is going to cover part of 11-5, which deals with alternating series, but I want to cover it at the very end because it is going to utilize some of the same things that we're going to discuss in the last section, section 11-11. Okay, so this 11-5 portion deals with the alternating series estimation theorem. Okay. Which is going to essentially allow us to take a few terms of an alternating series and use it to estimate the value of an infinite series to a desired accuracy. Okay, so what the alternating series estimation theorem states, it states that if S is equal to the sum of some alternating formula. Okay, so we have an alternating series where the formula looks like -1 raised to some power, which I wrote as -1 raised to the n power, times some formula b sub n. Okay, if that represents a convergent alternating series, then when we take the absolute value of r sub n, okay, so we're going to use r sub n to denote the remainder. We'll talk about what that means in a second. And if that is equal to the absolute value of S, which is the sum of the infinite series, minus S sub n, which is the sum of the first n terms. So we're going to take like a portion of the series, which is going to differ by the actual sum of the infinite series by some remainder. Okay. So that remainder is going to be less than or equal to b sub n plus 1, which we can use to denote the first neglected term in the series. Okay, so what this tells us is that the error is at most the size of the first neglected term. Okay, and what we can do with this alternating series estimation theorem is we can use this to approximate a partial sum so that it is correct to some desired accuracy. Okay, so for example, if we take the sum from 1 to infinity of the formula -1 raised to the n plus 1 power, times 1 over n. If I list out the first few terms of that summation, so when I plug 1 in the place of n, we're going to get -1 squared, which is 1, times 1 over 1, which is 1. Then when we plug 2 in, we get -1 to the third power, which is -1, times 1/2, which is -1/2. The next term is going to be positive 1/3. The next term is -1/4. The next term is positive 1/5. The next term is -1/6. Okay, so if I take the first 3 terms in that summation, so if I take 1 minus 1/2 plus 1/3, and I use that to estimate the value of that infinite series, those first 3 terms, if I use that to estimate the value of the infinite series, those first 3 terms are going to be correct to within an error of, at most, the absolute value of the first neglected term. Okay, so that first neglected term there is -1/4. The absolute value of -1/4 is 1/4, or 0.25. Okay, so if I use those first 3 terms to estimate the value of the sum, those first 3 terms, 1 minus 1/2 plus 1/3, that is going to be correct to within an error of at most the first neglected term, which is not a great estimation for us. Okay, we'll take a look at some other series where we can get an approximation that is pretty darn accurate for what we're doing. So if we were to go one more term, if I were to take 1 minus 1/2 plus 1/3 minus 1/4, that is going to be correct to within an error of, at most, the absolute value of the first neglected term, which is 1/5. Okay, so let's do a couple of examples here then illustrating this alternating series estimation theorem. Okay, so the directions ask us to approximate the sum correct to 4 decimal places. All right, so for our sum here, we have the sum from 1 to infinity of -1 raised to the n power times n divided by 8 raised to the nth power. Okay, so if we were to list out the first couple of terms of this summation here, okay, so when I plug 1 in the place of n, we're going to get -1 to the first power, which is going to make that first term negative. The numerator is going to be 1. The denominator is going to be 8 to the first power, which is 8. Okay, the next term, when we plug 2 in the place of n, will be -1 squared, which is +1. So that sign is going to be plus. We plug 2 in the place of n in the numerator, so we get 2 over 8 squared, which is 64. Okay, I'm not going to simplify the fractions. Okay, next term we get by plugging 3 in. Okay, so when we plug 3 in, we get -1 cubed, which is -1. The numerator is going to be 3 over 8 raised to the third power, which is 512. So it's clear that we are looking at an alternating series here. So if we want to approximate the sum correct to 4 decimal places, we want the first neglected term. So if you think about your decimal places, okay, the first decimal place is the tenths place, which is 1 over 10. The second decimal place is the hundredths place, which is 1 over 100. The third decimal place is the thousandths place, which is 1 over 1,000. The fourth decimal place is the 10,000ths decimal place, which is 1 over 10,000. So we want to keep listing terms here until we get a fraction such that the absolute value of that fraction is less than 1 over 10,000. Okay, so we want that first neglected term to be smaller than 1 over 10,000. Okay, so we need to keep adding terms to this alternating series until we get a term that is smaller than 1 over 10,000. So when we try the next term, when we plug 4 in the place of n, we get -1 to the fourth power, which is 1, times 4 over 8 raised to the fourth power, and 8 raised to the fourth power is 4,096, which is still not smaller than 1 over 10,000. So we have to keep going, okay? So the next term we get by plugging 5 in the place of n. So we get -1 raised to the fifth power, which makes that term negative. The numerator is going to be 5 over 8 raised to the fifth power, which is 32,768. And 5 over 32,768 is still not smaller than 1 over 10,000. So we need to add on another term. Okay, so we get the next term by evaluating that sum at n is equal to 6. So that's going to be -1 raised to the sixth power, which is going to make the next term positive. And then we get 6 over 8 raised to the sixth power, and 8 raised to the sixth power becomes 262,144. Okay, and 6 over 262,000 is like 1 over 40,000 and change. Okay, so this right here is smaller than 1 over 10,000. So that's going to be my first neglected term. Okay, so when I take these first 5 terms of the alternating series, when I add those things together, that is going to approximate the sum correct to 4 decimal places. Okay, so the value of this, again, we're using this to approximate the sum. So we're going to estimate the value of the sum. So when I total up all of these things here, all of these 5 terms, When we total those up, we get negative 0.098785. Okay, so when we use those first 5 terms to estimate the value of that infinite sum, that is going to be correct out to 4 decimal places. Okay, so that is how we utilize that alternating series estimation theorem. Okay, I want you guys to give this next example a try. So the directions here say to find the sum of the series, which is the sum from n is equal to 0 to infinity of negative 1 raised to the n power over n factorial. And we want that to be correct out to 3 decimal places. Okay, so I want you guys to pause the video while you work on that, and then we'll come back and discuss together. Okay, so taking a look at this one here, I want to start listing the first few terms of the summation. So when we plug 0 in, negative 1 to the 0 power is 1 divided by 0 factorial, that's 1. When I plug 1 in, we get negative 1 to the first power, which is negative 1 over 1 factorial. That's going to be negative 1. When I plug 2 in, we get negative 1 squared, which makes the numerator positive 1 over 2 factorial, which is 2. When we plug 3 in, we get negative 1 cubed, which is negative 1 over 3 factorial, which is 6. And if we want our sum to be correct out to 3 decimal places, we want to keep going until our first neglected term, again, 3 decimal places is tenths, hundredths, thousandths. We want to keep going until we get a fraction that is smaller than 1 over 1,000. Okay, so when we add the n is equal to 4 term, that's negative 1 to the 4th power, which is 1 over 4 factorial, which is 24. When we do the 5th term, that's going to become negative 1 over 5 factorial, which is negative 1 over 120. Next term will be positive 1 over 6 factorial, which is 720. And then the next term would be negative 1 over 7 factorial. And 7 factorial winds up becoming 5,040. Okay, and this fraction right here is smaller than 1 over 1,000. Okay, so that's our first neglected term. So when we add up the first 7 terms here, we're going to find those first 7 terms wind up approximating the value of that infinite series correct to 3 decimal places. Okay, so when you plug that into your calculator, the approximation for the series using those first 7 terms is going to be approximately 0.3680556. Again, that's an 8 that didn't come out very clear. Okay, so using the first 7 terms to approximate the value of that sum, that infinite sum, that is going to be correct out to 3 decimal places. Okay, and that's going to be it for the alternating series estimation theorem. You guys will have some homework problems that pertain to that. And then we're going to move on to our last lesson, which deals with applications of Taylor polynomials.